What's going on, everybody, and welcome to part 4 of the Deep Learning with PyTorch and Python tutorials. In this tutorial, what we're going to do is basically continue on with what we've got here. So we've talked about getting some data, which I think kind of cheated a little bit, but we've got data. We built our neural network. We passed some data through that neural network and got a response. But now what we want to talk about is actually how do we pass through, labeled data and actually train the model to hopefully be able to recognize whatever it is we're passing. So in this case, it's handwritten digits. So the idea is to get this model to the point where we can show it a digit it's never seen before, and hopefully it can predict and recognize, hey, that's a 7 or a 3 or a whatever it is. So yeah, let's get started. So in order to do that, there's two new concepts that we have to talk about. One is loss, and the other one is an optimizer. So when it comes to loss, this is just a measure of how wrong is the model. So our goal over time is to have loss decrease. So even if a model predicts correctly, in terms of argmax or whatever the output is, even if that's correct, chances are the model was at least wrong in some way. It wasn't perfect. It wasn't 100% confident in any of its predictions, and maybe it was 60% confident it was the thing that it did correctly predict, but it was also 20% confident it was something else. That's still not totally correct. There's some degree of error there because we want it to be 100% confident. So that's what loss is. And then the optimizer, what its job is to go through and adjust the weights based on the loss, based on these gradients. It wants to optimize and adjust all of the possible weights that it can adjust in such a way so as to lower the loss slowly over time. And that slowly over time is based on the learning rate that we use. So let's go ahead and make some imports, and then I'm going to briefly show some awesome imagery of learning rate. So import torch.optim as optim, and then we're going to say the optimizer equals optim.atom. And then atom is going to take, for now, two parameters. The first is going to be net.parameters. What's this? This corresponds to everything that is adjustable in our model. So there are things that don't necessarily have to be adjustable. So there might be layers in your neural network, and this is going to be true especially if you do transfer learning, where maybe you've got a model that's been trained on millions of images to detect classification or whatever. Those first few layers are going to be very good at very small and general types of image recognition tasks. And then the later layers are going to be very specific to the exact task that you trained it on. Well, what you could do is use transfer learning and freeze those first few layers and then only let the model or the optimizer adjust weights in like the last layers. And we'll talk a little bit more about transfer learning later on, but just know that that's a thing you can do. You can actually tell the network, hey, don't calculate gradients here, don't adjust these weights, and then only adjust certain weights in the model. But for now, we just basically it's everything because the default is to be adjustable. But like I said, we'll talk about later how you can actually freeze them and why you might want to do that. But anyway, so the first parameter is what is adjustable by this optimizer, and then we specify the learning rate. We're going to go with 0.001. You'll often see this 1e -3 as well. It just means the same thing. So what does that mean? What is this learning rate? How does it correspond to training times and how well the model's actually going to learn? For that, I've drawn this really beautiful, let's just call this the optimization curve. So the goal is to get here. Now, in order for your model to learn and actually get to this point, or in order for your model to learn, it doesn't necessarily have to get to that point. It could probably get to, this point and still do pretty good, still be pretty accurate at predicting things. But the goal is to get to this point. The learning rate, in part, dictates the size of the step that your optimizer will take to get to the best place. So anytime you pass data through this neural network, you get a loss. It is entirely calculable to determine what weights do we need for loss to be 0, right? To get perfect accuracy on the data we just sent. That is a simple mathematical operation. We could definitely do that. We don't want to do that because if we did that, that would be 100%. We're going to overfit to each batch that passes through, and we're going to just keep basically overfitting everything that comes through. So we use learning rate to tell the optimizer, optimize to lower the loss, but only take certain size steps. And then over time, as you take those steps, the steps that were taken, or the changes that were made that were just basically based on just the data passed, will kind of get overwritten. And what will remain as we go batch after batch after batch, what remains for us is the actual general principles. But anyway, I digress. Let's talk about the learning rate and step size. So let's say you've got this optimizer and you're telling it, hey, learn really fast, just go as quick as you can, take huge steps. Well, the problem is it's going to take steps like, this big, right? And then it gets here, 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 and then it just keeps, it can't get any lower than that, right? So if you have a learning rate that's too quick, too big, it's going to take these gigantic steps, and it's never actually going to get to the point we want to get. Conversely, if you have too small of a step that you're taking, you're just going to go bloop, and you're stuck here. You never got anywhere. So what you really need is something that's going to take just the right size step. So let's say it takes steps like this. It just slowly gets down where it needs to get. It gets over all these humps. Perfect. But there's really no way to have a priori knowledge of what is the perfect size step to get to this point. So what we do generally on more complicated tasks is we do what's called a decaying learning rate. And the way this works is it starts off with these gigantic steps, right? But over time, the learning rate slowly gets smaller and smaller. So it starts off taking these huge steps, might get stuck in this local minimum area, but then it gets smaller, right? And then it gets smaller and smaller. And then, so basically the idea is that'll help you descend this kind of mountain, I suppose, and get to where you want to go. Now, for a lot of problems, like I said, if you wound up here, even though you could get to this point, you'll be fine if you wind up here. And in the task that we're going to do right now, we are not going to decay the learning rate. It just adds more and more complexity. Eventually, we will be decaying learning rate because it's something you're going to have to do on most real problems. In a problem like this, it's a pretty easy to solve problem for the models, so we just don't need to. But we will talk about that, and that's what that means. I won't have to draw any more pictures. This might be the last picture I have to draw for you guys, so you're welcome. So anyway, we have our optimizer now, and again, all that we're going to do is we're going to calculate loss based on the output. So you get the model's output, you get the targeted output, the desired output, and you calculate how wrong is that, and then we apply that back to the entire network. We adjust the weights based on the loss, and then we just keep doing this. We just keep passing data, and then hopefully over time loss falls. And as loss falls, the expectation is that accuracy will also improve. But the model actually does not, we don't optimize for accuracy. We optimize for loss. It just so happens that accuracy follows. So let's get to it. So what we want to do is we want to iterate over all of our data, pass it through the model. But we also generally want to iterate at least a few times through our data. A full pass through our data is what's called an epoch, and we're going to say epochs equals 3. So we're going to make 3 whole passes through our entire data set. So then what I'm going to do is make some space here. Cool. What we want to say is for epoch in range of however many epochs we have, what do we want to do? Well, we're going to say for data in train set, and again, data is a batch. Data is a batch of features and labels, right? Or feature sets is probably the better thing to call that. A feature set has features. So you've got your features and your labels, or your targets, basically your classifications. So what we're going to say is capital X, comma, lowercase y equals data. So we're just going to unpack, because data basically is a, I think it'll be a tuple. I'm not really sure. I guess it would be a tuple. Someone even corrected me on this. Is it a list, maybe? Someone said I think it was a list. I don't know. I don't really use this for data. I'm only using it here because it simplifies it for tutorial purposes initially. Anyways, it's a container that contains 10 feature sets, and the feature sets are just grayscale pixel values, and then 10 targets, labels, whatever you want to call them. They're the class that basically says, hey, this is a 3, this is a 7, this is a 9, and so on. So XY data. So in fact, let me just print Y break. Print Y. Oh. So these are batches, unfortunately. So let's say Y0. And then, hey, let's just print X, capital X0 as well. Cool. So as you can see, this is your image. These are just rows of pixels, basically, that we're going to need to flatten. And then we come down here, and then you get the tensor. Hey, this is, if we were to graph this, it would look like a 4, and so on. Cool. So let me clear that. XY data. Awesome. Okay. So every time we calculate, or every time we run this kind of, every time we calculate loss and optimize the model, we want to start with kind of a, so every time we actually calculate and make these little gradients, so pretty much every time before you pass data through your neural network, what you want to do is net.0_gradient. Now, it could be the case, so for example, there's 2 reasons we batch our data. One is it increases or it decreases training time, so it goes faster, right, if we train in batches. But we don't want to pass the entire data set for reasons I brought up before already. But we also like batches because there is a law of diminishing returns here. But somewhere between usually 32 and maybe 128 of a batch size also helps to generalize. It's kind of two things going for us. So there could be times where you're on a very weak GPU or laptop, or maybe you're on a Raspberry Pi or something, and you're trying to train a model for who knows why, and you can only pass through one set of features and labels at a time. Well, this is going to be, it makes it very hard for the neural network to learn. So in theory, you could go around and you could, for every 10 samples or 10 things you pass through the model, then zero the gradient, and then calculate everything all over again. Because if you don't zero the gradient, they will just continue getting added together. So I guess PyTorch leaves this in your hands for, I suppose, niche cases, like where you can only actually pass one set of features and labels through your model at a time because you're on a small GPU or something, or CPU. But you want to still get the benefit of batch training. I'm not really sure, but anyways, just know we want to start at 0 with these gradients. And again, these gradients are basically, they're going to kind of contain your loss, like how wrong were you? And then your optimizer goes through and uses those gradients to try to optimize these weights. So net 0 grad, the next thing we're going to do is actually pass data through the network. So output is equal to net, and then we pass x dot view -1. You could also make this, you could just say, hey, it's whatever my batch size is, but in this case, -1 is fine. And then it's 28 by 28, so 784. Again, these are the dimensions of your image. Cool. I think that should all make pretty good sense to everybody. So once we've got output, what can we do? Well, we calculate, okay, how wrong were we? So what we're going to say is loss equals, and we'll use the functional and then NLL loss, and we're going to say output and y. And later in the series, we can talk about loss metrics and functions. For now, at least as a newcomer that I'm assuming many people are, just know there are kind of 2 major ways to calculate loss. One is based on one-hot vectors. So the output of our neural network is actually a one-hot vector, right? It comes out and you've got this vector, which it's actually not a one-hot vector, but the goal would be that it was. It's just not. But a one-hot vector is literally just like this array where one value is on, right? One is hot, one is on. So like something like this this is a one-hot vector. And if our input data or input targets, so the actual ground truth targets, if those were one hot, we would probably use mean squared error. That's generally the one I use. And then for regression, you would use probably something else. And then for, in this case, our metrics aren't one hot, right? It's a singular value. It's just a scalar value. So when your data is just a scalar value, you have to use a different loss metric. You couldn't use mean squared error. So just know going into it, just assume, like for now, again, we'll talk more, but if your data set is a scalar value like this, it's not a vector, right, with just one hot, just use NLL loss, okay? If your data is a one hot vector, use mean squared error. Cool. Like I said, we will talk more on that, and for sure we can get much more into that like when we do the neural network from scratch, but for now, I don't want to belabor loss metrics too much. All you really need to know is which loss is applicable to which environment and what is loss doing. That's it. So loss equal, okay, cool. So we've got our loss. Now what we want to do is backpropagate the loss. So we're going to say loss literally dot backward. Done. This is magical. Luckily, this is one of the things that PyTorch does just do for us. We don't actually have to do it, but you could. And again, that's one of the cool things about PyTorch is you could, not only can you do it, it would be pretty simple. You would just iterate over net.parameters, and then you could do at least stochastic gradient descent is pretty simple to do. I don't think I've never hand coded Atom, so I'm not really sure the Atom optimizer functionality there, but you could do anything you wanted. So you would just literally iterate over net.parameters and you could distribute it however you wanted. But for now, we just use loss.backward because we can. Then we're going to say optimizer.step. And this is what actually will adjust the weights for us. And that's basically it. So what I'm going to say is for data and trace set, cool. We'll just come down here and let's, at the end of this, let's just print loss. And this will give us the print loss. This will actually give us the loss value. I know this is not what everybody wants to see at the moment. We will talk about doing accuracy, but the goal is to see loss decline. So I'll just go ahead and get that to start running. Again, we are still running on the CPU, so things might not be super fast. I will be showing how to get on the GPU, and I will eventually be doing everything on the GPU, but just trying to introduce only a few things at a time, so yeah. This is actually taking surprisingly long. I kind of would have expected at least one output by now. Why are you taking so long? I'm not too sure. Okay, so we finally got a value. I don't know. That took so long. But anyway, this is our actual loss value for now. So the next thing that we're going to do while we wait on this to train, we can actually start coding the next stuff as this pops out. There's really no reason why we can't do it. I'm just kind of surprised at how slow that is. I really thought this would go faster. I've done this on the CPU. It normally isn't this slow. Anyway, so let's say we want to actually calculate. I'm just trying to think in my head, like, did I do something wrong? I don't know. But loss is going down, so that's a good sign. So anyway, while that's going, let's see how correct were we. So we're going to say correct equals 0. Total equals 0, and I know there's probably a way better way to do what I'm about to do, but anyway, whatever. And then what we're going to say is with torch.no_grad, what do we want to do? So there's two things that we can do. One, like I said, you can, for the layers in your neural network, you could say, hey, do not calc gradients on these layers. But you also can say with torch.noGrad or no gradients, do something. So in this case, when we're trying to validate our data, we actually don't want gradients to be calculated. This is supposed to be out of sample data. This is testing data. We just want to see how right or wrong is the model. We don't actually want to optimize based on this data. So we're saying with torch.noGrad because we don't want to calc gradients here. We just want to know how good is the network at this point. So we're going to say with, again, I'm not a PyTorch expert, so just take this with a grain of salt, but I'm pretty sure historically there's been, like, whatever your model is called. So in our case, it would be like net net.train, I think. And then there was also like net.eval, I think. And what this did was based on your parent class here, I think is where it was pulling from. This would dictate whether your model was in training mode or eval mode, or evaluate, basically to do validation. I never saw this in the actual PyTorch documentations that I went through. I think that's old. Like, I don't think that's a thing you need to do anymore. I could be wrong. But if you're looking at people's code historically, that's where I was seeing it in other people's GitHub code and stuff like that. I was seeing this .train, and it was usually in the forward method, I think. I could be mistaken. I forget where I was seeing it, but I was like, what's that? So I tried to look into it and see what was going on there. And I think this has basically just replaced these two calls. I could be mistaken. I'm sure somebody will tell me if I'm right or wrong there. But anyway, just take note that that was also a thing. And at least in my findings, I haven't found that it matters if I don't use these. So I think it was just part of old PyTorch, but you'll still find it in people's code. Anyway, continuing along, so with proportional gradient, what do we want to do? Well, we want to say for data in train set, what do we want to do? So we're going to say, again, x, y equals data, and then we'll say output is our network, and then it's x.view, and again, -1, 784, or 28 by 28, whatever. Anyway, the size of our images. So we have our output, and then what we want to do is we want to compare is the argmax, because again, our targets are scalar values, but the neural network outputs an argmax. So what we want to say is we'll say idx I in enumerate, and we'll just enumerate over the output. Again, there's probably a way better way to do this, but we're just going to do this for now. If torch.argmax I is equal to the index value that we're on, so y index, whoops. If that's the case, we'll say correct plus equals 1. Regardless, we're going to say total plus equals 1. And then we'll just print accuracy. And then we will do correct out of total. And let's say, let's do a round here. Round correct out of total 3. Okay, so that'll give us a decimal accuracy. So basically what we're doing is this was a batch of information. So then what we're going to do is we're going to compare. There probably is a way to compare these two things. I can think of better ways to do it if both were one hot or scalar values. I can think of some quicker ways. But anyways, all we're doing is we're just going to say, hey, for every prediction that we made, does it match the actual target value? If it does, hey, we got it correct. Either way, we total. So what do we do? So let's go ahead and run this. This is also slow. We need to be on the GPU. Bad. While we wait on that, shout out to long-term channel members Igor Malinov, Faust, Florian Linsheed, Werther's Original, Alan, Wang, Daniel Cucchiello, Magali, Drew Mayer, Wheatgrass, NJR, 1762, and Misk. And of course, the OGest of all the members, the longest-term member, Stenosko. Thank you, everybody, for your support. 15 months is basically forever. You guys are amazing. Okay, we got an accuracy of 97.5%. So we did really well. Unless we somehow cheated. I don't think we did. But one thing I will tell you is it's really, really easy to cheat with neural networks. And I don't mean actually cheat, but to miss something little. So there's lots of ways you can sneak in little biases without realizing what you're doing. And again, the neural network doesn't understand, oh, I shouldn't actually be using this information. If it's useful to figuring out what the accuracy is, whether it has some direct relationship with the target, or it could be something way more obscure than that, like an imbalance issue or whatever, just know that normally seeing an accuracy this high should be a major red flag. This is valid for this task, but for most real-life tasks, you will never see an accuracy this high, especially if the distribution is like 10 classes or something like that. This is very difficult to get. In this case, it probably is legitimate, but be wary. Be very wary. So, so for example, as we iterated, the last batch will still be stored as x's and y's. So if we just print x out, like I said before, there it is. So what if we did import matplotlib.pyplot as plt, and then we'll just say plt.imshow, and we'll say x 0, and then we'll say .view as a 28 by 28, so we'll get it back to be an image, hopefully. And then we'll do a plt.show. Run it one more time. I know there's a way to do a matplotlib inline, but hey, whatever. Okay, that's a 0. That's actually a pretty hard, that's like a very slanty 0. It'll be interesting if we actually got this right. But what we'll say is now print torch.argmax. And in fact, we actually could say it would be the 0th prediction. So output 0, I guess. But we could also pass it through. So we could say torch.argmax of net, and then we'll pass into the network x0 dot view. We need to reshape it again to be a -1 784. And then remember, we input a list, we get a list back. So we need to say the 0th element. Cool, it's a 0. So it actually got the prediction right. Let's try x1 and 1. So let's look at it. What the heck? That could be a 6 or a 0. I would say it's a 0, but that's a really hard one. I've seen some crazy stuff in these ImageNet or ImageNet MNIST datasets. Anyway, I would be happy if it said 6 or 0, to be honest with you guys. Let's check 2 here. Let's see what this one is. Hopefully it's a better one. 1. These are crazy hard, but again, it got it right. Let's do the 3rd index here. Okay, that's clearly a 6, and so on. We could go on like this forever. I think we should move on to the next model. It's very tempting to like open Paint and hand draw a digit and then load it in and see if the model gets it right. Maybe down the line we can do that. Like a lot of people have historically requested, please show us how to actually run a model on a server. So I think maybe I'll save that, and maybe we'll have like a little GUI or something where people can hand draw a digit and then we output the prediction or something like that. And that would mean the model is running in the cloud and then it makes the prediction and so on. So I think we'll do that. I know some of you guys really want to see it. so just know that maybe I'll incorporate it that way, and we'll actually host this model. But anyway, I think we've learned a lot of basic stuff, but the problem is with your knowledge up to this point, this was really cool, but you can't quite apply it yet because we kind of cheated. We used our own data set. Also, it was like everything was just done for us, including things like balance issues and normalization issues. Like again, these images were already, for example, scaled for us. So the images were automatically grayscaled and scaled between 0 and 1 for every pixel value and so on. There's a lot of stuff that was just done for us that if you tried to take what you know right now and apply it to some other use case, especially with imagery, but even other kind of tasks that you might want to do, chances are you'd have a really hard time. So what we're going to do is leave MNIST and leave cheating behind, and we're going to grab, we're still going to grab a pre-made data set because building your own data set is absurd. So we're still going to grab a pre-made data set, but it's raw images, and we're going to build a new type of model, which is a convolutional neural network, which is traditionally used for imagery, but actually convolutional neural networks are kind of taking over. In fact, I'm not even sure I'm going to teach recurrent neural networks in this series because the things recurrent neural networks were being used for, like sequences of data, we're actually kind of finding convolutional neural networks are doing better. So So we'll see what I decide to do there. I really haven't made up my mind. So anyway, that's all for now. If you've got questions, comments, concerns, whatever, feel free to leave them below. Hopefully you guys are enjoying the series. I'm enjoying working with PyTorch. I think it's a pretty cool library. It can get tedious to do some of these things. The other thing I'll bring up, if I forget to mention it, I probably will also cover this in this series. There is a library called Ignite, which I guess makes the training loop easier, because that's the most tedious thing with PyTorch, is the whole training loop that you've got to code all this. It's highly likely you'll make a mistake somewhere. So there is a package for that. The other thing is, like, there's so much stuff that we've not taught yet because I just trying to do a little bit at a time. But some of the things that we have to pay attention to are, like, as you train, comparing validation accuracy to in-sample accuracy is really important. Also, we probably like to graph loss over time as we learn. There's so much to learn, so much more to go. Anyway, I think I'm going to stop it here. Questions, comments, concerns, leave them below. You can also join us in the Discord. It's discord.gg/Sentex. Otherwise, I will see you guys in the next video where we have so much more to learn.